Become a sustaining member of the Commonwealth Club for just $10 a month. Join today.
Welcome to the Commonwealth Club. I'm George Hammond, Chair of the Humanities Forum, which organized today's event in association with both Wonderfest and as part of our Good Lit series that's funded by the Bernard Osher Foundation. I'd like to welcome Ashley Jean Yeager, the science writer and the author of Bright Galaxies, Dark Matter and Beyond. It's the story of the life of astronomer Vera Rubin. This is one of our over 600 programs that we've done since the pandemic started, where we're doing it without an audience, but bringing to you all of the audience, for all of the audiences that listen to podcasts and our YouTube channel, Facebook, the programs that we brought to you live here in San Francisco before the pandemic, and that hopefully will be coming back very soon. But now, let's talk to Ashley about this very interesting story about a female astronomer from the 20th century who was one of the first scientists who kind of supported the idea of dark matter. So Ashley, first, welcome to the Commonwealth Club and a great book. Wonderful, wonderful job.
Thank you so much for having me. I'm so excited and honored to be here.
Good. So let's start with a little bit of background about Vera. So we have this woman fighting against the old boys club, basically, to make progress, very successful at it. Well, let's just give an idea about the span of her life. I mean, she only passed away a few years ago, in her 80s, I think, but really got active early on, and maybe we can set up how she did this.
Yeah. So Vera Rubin was born in the 1920s. She grew up mostly in Washington, D.C., and at the age of about 10, I guess you could say, she was sharing a room with her sister and looked over, and there were these row of windows in their bedroom, and she just became fascinated by the stars. She would spend every night looking out the window, watching the stars, tracing their paths across the night sky. And while she was doing this, she was trying to read about scientists, so Benjamin Franklin, Isaac Newton, and she also came across the story of Maria Mitchell, who really kind of put professional astronomy on the map for the United States. Maria Mitchell discovered a comet with a telescope, and because of that was awarded a medal from the King of Denmark, and then went on to found an observatory at Vassar College. And so Vera learned about all of these different stories and then eventually ended up at Vassar to study astronomy. And
one thing that's important about that, you studied astronomy at Vassar. How big was the department?
She was the only student in the department. Yes.
I thought that should be made clear. It's a different time.
Yes, this was the 1940s, just after the World War II had ended, and she was the only astronomy major at the time. And so,
but they had a little observatory, right? They had a little observatory and a professor, so that's not too bad.
They did. Yeah. They did. They had a little observatory, and that was actually kind of where she got some of her first hands-on experience, going out and making photographic plates of the night sky and different objects in the night sky. And I think kind of where she really learned to love kind of going through that process of making those observations. And about the same time, she ended up meeting Robert Rubin, who became her husband. And he was a graduate student at Cornell at the time. And as Vera was thinking about what her next steps were, she had applied to Harvard. She had applied to several other universities to do her graduate work in astronomy, and ultimately decided to go to Cornell with Bob. And I think this is something that I talk about in the book. This was kind of a really, I think, fundamental decision that in some ways put her on the path to being this luminary in astronomy, because she was able to ask questions as a graduate student that maybe she wouldn't have been encouraged to ask at a place like Harvard or Princeton. She kind of had that intellectual or creative freedom to dig into something very different than a traditional question. And actually the question she asked was, does the universe rotate? Which is, something that's incredible to think about. And her logic made sense in asking that question. It was something that George Gamow, one of the kind of big name cosmologists at the time, had posited. And the idea was, everything rotates, right? Planets rotate around, they orbit the sun, stars and galaxies orbit a galaxy. So why wouldn't galaxies orbit a kind of center point in the universe? And so she really went after that question and tried to collect data to find an answer. And she did find some
It's pretty
unexplained.
bold to think that you can get any data to support an answer on that, right?
Right. Yes, exactly. Especially at that time. I mean, this is late 1940s now. You're just starting to have these galaxy surveys where you're starting to see kind of threads of long tendrils of galaxies, some of the beginnings of the large scale structure of the universe starting to emerge. And so she was trying to kind of get the different velocities of galaxies as they move through the universe to look for this universal rotation. And she did find some kind of strange, unusual, unexplainable behavior. And she presented that at one of the big astronomy meetings, and kind of got the reaction that no one really believed her. They were like, no, this can't be right.
Right.
This you don't have the data to make this claim. You need to go back and do more work. And so I think that kind of really stuck with her as a criticism of like, okay, I constantly will need more data to confirm whatever conclusion I draw. And you have to remember at this time, she wasn't able to go to the telescope herself. There were no facilities that were open to women in the late 40s, early 1950s.
Just out of habit that they didn't do it, or are there very few astronomers that were women, or what? Is there anything in the basis for why that was true so late? Because it's fairly late, in the 40s and 50s to say women can't go and look into that. Was it just a habit, like in accounting or something like that, where there were so few women as well?
I think I think you could say that, but then there were also arguments that there weren't really facilities for women. So one of the kind of famous stories for Vera is about this bathroom at Palomar Observatory and how essentially the application said women can apply because we don't have the facilities to accommodate women. And so that kind of segmented everything just for men.
So all they needed was an all-gender bathroom and everything would have been fine.
Exactly.
It's so tough to solve some of these problems, right? You think, how difficult was that? Anyway, go ahead.
Yeah.
But it's true. It's
right.
funny. It's just a funny thing that people use as a block to stop something from happening, basically.
Yes. Absolutely.
So, sorry to interrupt the story, but it's a very interesting part of the story is what stopped her, such tiny little, apparently tiny little things, but
Yeah. And she actually had this memory of going to Lowell Observatory when she was a graduate student. And she saw all these male astronomers making observations and kind of publishing all these papers. And it made her feel inadequate. It made her really question, they're so far ahead of me. Can I actually do this given the limitations that I have? And so that was kind of always a question in the back of her mind. And for some reason, she pushed forward and kept trying to challenge it. And I think a lot of that was from support from her husband. He very much wanted her to have a career and made a lot of decisions to make that possible for her.
So she breaks through eventually and says, okay, I'm, and each step of the way, it's basically that she does something fairly outstanding and makes a presentation. And each time there's more data, it's more convincing, it's a little bit more reliable. People are getting used to the fact she's a woman doing this, right? And so eventually she breaks through. But it takes how long before she actually gets time on the things? I think in the 60s, if I remember correctly, it took until then, right?
Yeah, it really, she really wasn't able to go and observe until the early 1960s. And so I think that was the beginning. And I think, she really coveted being at the telescope because it was so sacred almost.
Yeah.
So what happens is Kitt Peak National Observatory in Arizona opens. And when it does open, it's open to women. So she applies for time there. And around the same time, her husband has the opportunity to go on sabbatical and picks to go to La Jolla, California. And where he picks to go, the Burbidges, Margaret and Jeffrey Burbidge, are there. And they're kind of, world-renowned astronomers at this point, mainly for their contribution to understanding how stars make their energy. And so Vera asks them if she can work with them, and that's another opportunity to go to the telescope with them. And she kind of gains more skills, and that's where she really starts working on the question that will become her central thesis that kind of gets us to the point of understanding that the universe is made of stuff that we still don't understand. And what happens is Jeffrey and Margaret Burbidge are looking at galaxies, and they're looking at how stars orbit the galaxy, what speed they have kind of going around the center of the galaxy. And they're looking mainly at stars close into the center of the galaxy and recording those speeds. And the assumption is at that time that, they're only going to look at stars a certain distance from the center of the galaxy because, just like in the solar system, the speeds of stars farther out will drop off. And that is just what everyone assumed. It was written in papers over and over again. And no one really said, hey, let's try to find stars farther out from the center of the galaxy.
Right.
And so then,
the example was that the solar system, the solar system, the planets the speeds do drop off. Why don't you describe, this is a really big issue, and why don't you describe what it is? There's a central, in the case of the solar system, there's a central sun, and then there's the planets going around it. But everyone's familiar with Crack the Whip, for example. This game, and of course the outside person ends up going faster than they possibly can and goes flying off. So there is something like that going on in a solar system, and they assumed it would be true for galaxies. So that's the basis for their assumption, and it's easier to do the stars closer, and so that's all they did. But Vera said, let's look at this differently. So go ahead. I'm sorry.
Oh, no, that was a great explanation.
So why is it that in the solar system, not why, but in the solar system, when the planets go around, they go at different speeds? So everybody made this assumption.
Yeah. So, Pluto is very, very far from the sun. And so the gravity on it is not as great. And so it kind of just plods along. Well, if you look at Mercury is kind of very close in, and it's just whipping around the sun super fast.
Right.
And so it's basically kind of what's pulling on those planets, and just the difference in the amount of gravity that you have to kind of affect those speeds.
We'll get to this a little bit later, but in the galaxies, the central core, whatever it is, some people think black holes, some people think other things, but the central core of a spinning galaxy is only a small percentage of all the mass in the galaxy.
Right.
Whereas in the solar system, our sun is something like over 99% of the mass in the solar system,
Right.
and therefore that might be part of the picture too. So.
Yes.
Okay, so everyone made this assumption, and Vera, that the galaxies would behave the way the solar system did, and Vera wasn't so sure. This is her big contribution into the dark matter thing. So we'll
Yes.
look at the research in a little while, but tell a little bit more about how she went about doing this then.
Right.
Because she's no longer looking at does the universe spin.
No.
She's now on to this issue. This is what she studied. Yeah.
Yeah. She, after asking that question about whether the universe spun, she kind of really got into how an individual galaxy spins. And so that's kind of how she gets to this point of looking at these different stars to understand how a galaxy is put together. And so she does. She starts to question this assumption, and really with her students at Georgetown, because she did her PhD at Georgetown and then ended up staying on as faculty there and took on some students. And they actually helped her first start to ask this question about the Milky Way, so our own galaxy that we're in, really trying to find stars very, very far from the center of the galaxy and much farther than where the sun sits from the center of the galaxy, and try to kind of understand, do these stars move quickly? Do they move kind of more slowly? Do they plod along? And our galaxy is kind of hard to work with because we're inside of it. So it makes it very hard to get a sense of what's going on.
I thought that was a very interesting part of your story. Was the people were much more confused about the Milky Way and trying to figure out what's going on than the ones that were much more distant, because you can look at it from the outside, and they learned much more about galaxies from the further away galaxies, and then applied it to the Milky Way and tried to figure out if it's true here. I thought that was interesting. Didn't know that.
Yeah. So she's asking this question. She's working with her students and also had been influenced by the Burbages. And she gets to this point where she's kind of juggling a lot of different things. She's juggling teaching. She's juggling going to the observatory and doing her research, her family, kind of trying to figure out how to navigate departmental politics. And so she gets to a point that she feels like, okay, something's got to give here. Mm-hmm. And she decides that the thing that she would want to give up is teaching. So she goes and asks for a job at the Department of Terrestrial Magnetism, which is part of the Carnegie Institute. And there are researchers there who are asking the same question about galaxies, and they're working in radio astronomy, radio wavelengths. Mm-hmm. And she's working in the visible wavelengths, what we can see. And so after some deliberation, they finally do decide to hire her. Mm-hmm. She's the first female staff scientist at the department. And that leads for some interesting onboarding practices, which happened to happen on April Fool's Day, April 1st. So she shows up and they have no paperwork for her. And of course, at first they think she's a secretary, and she has to explain, like, no, I'm a staff scientist. And what was really interesting, and I think, again, a kind of crucial moment in her career, is the director at the time had set up two offices for her. He had set up one office with one of the radio astronomers, and then he had set up another office for her with this very gifted instrumentalist, Kent Ford, who was creating this device that was essentially would take photons from very faint objects and magnify them so that you could see stars very, very far away, which became key to Vera's work. And so she moved in with Kent Ford. And he told me several years, a long time later, many decades later, that she just never moved out. So that's the start of the beginning of their collaboration. And what she did with him is she used this instrument that he had to look for very faint stars in our neighboring galaxy, Andromeda, and start to track the speeds of those stars as they orbited the galaxy. Mm-hmm. And this was late 1960s. And she starts to notice something very odd, even in some of the first observations that they make, that those stars far out aren't doing what they're supposed to be doing. They're moving way too fast for, if you were using the assumption that the galaxy would work like a solar system. And we could actually, show one of these slides here.
Okay, great. You can get up the slides that she has.
Yeah.
Okay, great.
So this starts to get into the meat of Vera's work. These are called rotation curves. And so essentially what you're seeing is you're seeing the Andromeda Galaxy, M31, as it's labeled there. And on the x-axis, this is the distance of a star is from the center of the galaxy. And on the y-axis, you're looking at how quickly that star orbits the center of the galaxy. And so if you were following kind of that solar system assumption, what you would think that you would see is the curve would kind of go up, dip, go up again, and then drop off and have the stars really far out, kind of going really, really slow around the center of the galaxy. But what you see here, and this is what Vera started to observe, is that didn't happen. The speeds didn't drop off. Those stars really far out were zooming around the galaxy at roughly the same speeds as stars much closer in. And so that kind of raised
for clarification's sake. So we have a center and we have this distance way out here on the chart, the ones that are way out of the galaxy. I'm going to talk about something about that in a second. But the speed that they're going, 200 something kilometers per second, whatever, that's the same or relatively the same as the stars in, but they have a much bigger distance to go around. So they're not going around in a crack the whip sort of fashion. They're going around at the same speed. And so they're orbiting the center of the galaxy still takes them much, much longer than the ones that are at the center. Do I have that right?
You have that right.
Okay,
yes.
great. And I think the other thing that's interesting about the picture is you talk about it in your book. When we think about galaxies, we're thinking about the central thing with the cloud of stars around it. But you're saying that every galaxy is actually a big a spherical halo that goes this far out. So galaxies, in addition to solar systems, have a central core. And at the core of the galaxy is even a deeper core, but then all the stars that we see, that's still pretty much the center of the galaxy, and that the galaxy is surrounded by stuff for hundreds of millions of light years around it or whatever, that are still in its orbit.
Yes.
Is that right? Okay, so that makes it clear from the picture here, because it looks like these things are outside the galaxy, but you're saying that's really part of the galaxy system still.
Right.
Okay.
Right. Yeah. So this kind of starts to get to this question that she and others were stumbling on in the late 1960s, early 1970s, is that you have these objects really, really far out, kind of farther than where you can see the galaxy, and they are moving way faster than astronomers would have expected. And so, people start to question, like, what's going on here? Like, why are these objects super far out moving so fast? And what they're starting to think about is like, okay, if this data is true, if these numbers are true, then something out there has to be pulling on those stars. Something has to be revving them up, just pulling them along, making them go super, super fast. Otherwise, they wouldn't be able to kind of stay in the galaxy. They would just be flying off into space. And so at about this time, you have theorists who are, they see these observations, they see some other observations about galaxies in clusters also moving rather quickly. And so there comes this point where researchers start to talk about dark matter. And in reality, dark matter, the term was really kind of coined in the early 20th century as researchers were looking at individual galaxies and also these clusters of galaxies. And they had this sense that things weren't operating the way astronomers had assumed, that there might be something else out there, whether it's stars that we can't yet detect, whether it's something unknown that we don't know, but there might be this stuff that's pulling everything along, making things move faster, making galaxies interact in ways that we don't understand.
At the beginning, the assumption, it sounded like from what you wrote, that the assumption was it was more like dead stars, the matter of dead stars, old planets, sort of like the equivalent of asteroid belts. I mean, that kind of thing that you don't really see these things because what you see is the light. But I mean, if you look at a galaxy, there's all these dark spots, and that could be filled with stuff that's not luminous. So luminous matter is one thing, non-luminous matter. So it wasn't quite so mysterious as it is now, where we kind of have no idea what this is, because everything that people have thought might be dark matter, like all the way down to neutrinos, doesn't seem to be the thing that makes the numbers come out right? So
yes, absolutely.
So it got more mysterious as time went on.
It did. It got more mysterious as time went on. That's right. Yep. So you kind of had these rumblings about dark matter in the 1920s, 1930s, but no one really took it seriously, unfortunately. People just thought, oh, how can the universe be made of stuff we can't see? Those observations must be wrong. And really, when Vera returned to this question in the 1970s, she kind of got the same reaction. There were some theorists who were starting to piece together that maybe galaxies had more matter, that maybe they kind of had this spherical halo that encompassed them. But it kind of wasn't a mainstream idea yet. It was, you had all these different pieces to suggest that the universe was playing these tricks on us, but not everyone was on solid ground that this was really happening. And so I guess what happens is Vera publishes these results. She gets some pushback to people saying, oh, well, that's just Andromeda. That's just our neighbor. Maybe it's an outlier. You really have to, you need more data. You really have to do this in other galaxies. To which she says, fine, I will go do that. And she does. And so, late 1970s, she's starting to put this observing program together. And you have to remember, this is really hard. You're looking for stars and galaxies very, very far away. You're trying to measure how quickly they move around that galaxy. And you can't just use one or two stars, like you have to have several stars in that galaxy. So it's a tall order, but she just becomes determined that she will do it. And so if you want to show the next slide, she starts to do this in galaxy after galaxy. And at first, she has 5 galaxies where she sees the same pattern, right? You can, these are all curves, rotation curves of different galaxies. And essentially you see the same thing, the speed starts to go up, and then in the most part, they level off, meaning those stars, again, very far out, are traveling much faster than what you would expect if you're kind of using that assumption of Newtonian gravity and the idea of the model of the solar system. And so you can see here, this is kind of 1980, and I think there are 22 galaxies on there. And again, all a very similar pattern, all still kind of showing that flat rotation curve. And what she's showing is there's small galaxies, they're mid-sized galaxies, and then kind of down in the bottom, you can see one called UGC 2885. And that is one of the largest spiral galaxies in the universe. And you have that same pattern. So, that galaxy is massively wide. And even very, very far out at the edge of that galaxy, those stars are still moving super fast. So this paper with this data came out in the 1980s, early 1980. And at this point, there had been the theoretical work. There had been 2 astronomers who had written review articles saying, we need to take the idea of dark matter seriously. And then I think with Vera coming along and saying, this isn't just something that we see in 1 or 2 galaxies. This is something that we see in 20, 30, 40, maybe even 100 galaxies. I think the astronomy community kind of had to take a step back and say, okay, we really need to take this issue seriously. We really need to start thinking about what these data are telling us and how it's going to reshape what we think about the universe. Because essentially what all of this is telling us is that most of the matter that we've been looking at, this luminous matter, really only makes up a small portion of the matter that's in the universe. So essentially we've been tricked, and Vera actually said this. We've been tricked. The universe has played a trick on us, that we've been looking at this one thing, and the rest has been hidden, and we really don't know what it is yet. And so that kind of opened the floodgates for researchers to really start thinking about, is dark matter made of dead stars and planets and kind of some of these other objects that we know about that we can't see, or is there something else? And so in the 1980s, you get to this point where there's kind of two camps, and they're starting to collect all this different data to try to understand, what is it that's tugging on these stars? What is this dark matter? Because now we have to accept that it exists.
She's making this contribution in the 1980s. She's now 60 years old. That's also unusual, right? I mean, she's in her 60s or getting to that area, right? And so that's another unusual thing. Scientists usually make their great contributions a little earlier than that. So, and she kept working on it, you know. So there's more. She just kept being productive.
Yes, absolutely.
It's very interesting.
So I mean, even the galaxy that I showed you, or the one that I pointed out there, UGC 2885, that's the next slide I have. I actually have a picture of it. And this is Vera Rubin's galaxy. It's actually named after her. And even into the 2000s, early 2000s, Vera was still looking at this galaxy, still looking for the farthest stars that she could find, because she wanted to check that her data were correct. And she wanted to know, like, how far out do you have to go before stars' speeds around the galaxy might drop off? Is there a point where you get that curve that's flat and then it starts to level off and then it starts to dip back down, right? Because then if that's true in how the galaxy is put together, you might get to the point where you're running low on dark matter. And so there's not that matter to tug on those stars. Or the other thing that she proposed that I thought was really fascinating is, like, maybe the dark matter halos continue and they actually touch other galaxies. So, you know, our dark matter halo could be touching Andromeda's dark matter halo. And there's been evidence now to suggest that that's not the case. But the fact that she was still curious well into her 70s to ask those questions and try to find those answers, I thought really just spoke to how curious she was about the universe and about the world around her, and really trying to understand what's going on. And you know, just not ever losing that kind of childhood curiosity.
So sort of like a science writer.
Yeah, that's true.
So as a science writer, you look at this picture, you know, and I see these pictures of the galaxies and I say, you know, have scientists ever tried to compare this motion and those speeds to fluid dynamics? Because it looks like it's all going down the drain. You know, if you like, there's a drain in the center and it's all going around it and it's going down the drain. Now we know that there's black holes there. And so it's not a drain going down into nothing, but there's a circular thing that acts like a drain that we know is there. And so that might be, I mean, the motion of the particles may be much more similar to fluid dynamics than other things. So anyway.
Yeah. No, I think that's true. I mean, I think there are so many different connections from lots of different fields. And that's one of the beauties of actually being a science writer, is that you can go and kind of make these different relationships between the different fields of science. And actually, I think that's something that can make the experience and also your writing much more rich, is if you can draw from these different types of sciences, like, you know, kind of applying fluid dynamics or other types of research. When you just look at something like this, it really blows your mind that we can actually understand some of these things.
Why don't you talk a little bit about, you know, how you got into science writing and everything, because we've kind of covered Vera. Well, I want to get back to the ideas that she discussed in a little while, but this is something that obviously, you know, you've done with your life, and you've covered a whole bunch of different sciences. And as you said, you do walk away from one. If you do that, you walk away from one science to the other. This this is the analogy that they like over here. This is the analogy they like over here. And sometimes they're useful in other places. So why don't you tell us a little bit about your journey?
Sure. So I guess I had kind of always been interested in science as a child. My parents were both high school science teachers. And so I spent a lot of time in their classrooms, and they did a lot of hands-on experiments with their students. So I spent a lot of time in their labs doing different things, splitting chlorophyll into its component colors and doing the flame test, where you look at the colors of different elements and what they show. And so I always had the fascination, and I did a lot of science fair projects as a high school student. And I always really liked writing the background section.
I'll bet you were popular on your team. Because
yes. Yeah.
That's not the choice of everybody.
Yeah. And I mean, I loved doing the experiments too. That was fun. But for me, it was like, how do all these ideas fit together? What's the history? Where does this come from? And so at the same time, I started to do a bit of journalism. I was actually covering sports because I was also an athlete. And I went to the University of Tennessee, and I was a swimmer there. And they actually had, at the undergraduate level, a program in science writing in the journalism school, which is very rare. And I had an advisor who was very wise and realized that I liked writing and realized that I liked science. And she was like, I think this is a perfect profession for you. And so I took one of the first classes, which was actually called Science Writing as Literature. It was taught and still is taught by Dr. Mark Littman. And I just fell in love with the idea that you could make science a beautiful story, because you could learn so much and still kind of make it feel like you were reading a fiction book. But you were learning all this science along the way. And so I kind of started to do some science writing. I went and I worked at the Air and Space Museum after I had graduated from college. And it was there that I discovered Vera's story. I was walking around one of the exhibits, and I was getting prepared for actually being an educator on the floor and interacting with guests and trying to engage them in the different exhibits. And so as I was walking around, I noticed that the Explore the Universe exhibit there actually didn't have many women, but there was one that I stumbled on. And, she had these very, curious looking owl glasses and seemed very serious. And as I started reading, it talked about dark matter. And I had never heard of dark matter. At this point, I'm 22, I'm very young, I'm very green, I don't know what I'm doing. And to kind of think about the idea that most of the universe is made up of stuff that we don't understand. That just blew my mind. And let alone that this woman had some hand in convincing the astronomy community that that's what the universe was made of. I just had so many questions. And so I started peppering my advisor with questions. And eventually he said, well, I am working on Vera Rubin's oral history. Would you like to come with me to interview her? And I, as a young science writer, like, absolutely. Oh my gosh, this is kind of a once in a lifetime opportunity. So I jumped at the chance, and we did. We spent a day with Vera. We actually got to interview her husband along with her. And that interaction, just the way she was so welcoming and so gracious and so patient with all of the questions that I had. For some reason, I was going on to grad school in science writing, and we had to work on a longer piece. And one of my advisors there suggested that I write about Vera. And so I kind of made the decision to send Vera an email kind of randomly after I had done the interview over the summer and ask if I could come to the telescope with her. And I thought she would say no. I thought for sure she would be like, no, it's just not a good idea. I want to focus on my work. I don't want any distractions. And she called me. I mean, I sent her an email, and she called me. And she said, I am willing to let you come to the telescope with me, but I do have some expectations of you, right? That basically, this is a very serious time. I don't want to be interrupted while I'm working. So we kind of talked out all of the logistics. And before I knew it, I was going to the telescope with her. And so that kind of all got worked into a thesis, it was a 10,000 word piece about her. Mm-hmm. And I wrote that. I finished my graduate degree, and then I didn't really think anything of it from there. And then probably, 10 years later, MIT Press reached out and said that they were doing this new series on women in science. And they had read my thesis and would I be interested in transforming that into a biography? And mm-hmm. I said, absolutely. And that kind of is what led to the deeper dive into her work and really understanding who she was as a person and trying to communicate that, not just for astronomers, but for everybody, just mm-hmm. the curiosity that made her who she was, and also the principles she lived by that I think really made her successful.
Yes, well, those advisors were spot on in giving you a good plan, because that certainly worked. Now we have a lot of questions that have already come in, so excellent. We'll cover those, and then I have some other plans about some of the ideas, but we'll do this first. We'll get the audience's questions in. Sure. So from one of our sponsors, Wonderfest Science, every scientist may be disappointed by the slow recognition of his unusual findings. In her life, did Vera Rubin express such disappointment with special vigor, or did she accept it?
I don't know that she was disappointed. I mean, I guess maybe perhaps you could say that. She was very outspoken about her work and the contributions she made. And I think she wanted to use that as an example of trying to encourage more women to go into the sciences, because I think there was some hesitation there. So I think perhaps there was some frustration that she did express, but I think most of her focus was really on trying to make people excited about science and make them curious and kind of draw them in. And she did address that there are challenges and there are things that you have to work through. And I think by her example, she gave women some of the tools that she used to be successful. Stay curious, stay hungry. If people doubt you, keep working. And I think the biggest one is surround yourself with the people who really are there to help you, and kind of just ignore or block out the people who are trying to bring you down. Because if you really tap into that network of supporters, that's really going to be beneficial and kind of help you get where you're going to go.
Yeah, as the question implied, I mean, it's true for men and women, but obviously when you have the extra cultural pushback against women, it's much harder, and now that pushback is a lot lighter, right. And so it's a little easier, et cetera, but it's not over yet. We're not just saying, and it's kind of ironic, because you'd think at this point that everybody was saying, why would we waste any of our intellectual resources? But human beings are not willing to be that light and easy about anything, I think. So
that's true.
So I have another question. Since the Big Bang, non-dark matter has clumped into galaxies, stars, and planets. Do we understand why dark matter seems to have remained more dispersed?
I think slowly it's starting to become better understood, but I think because there's so many questions about dark matter that we still have, it is harder. There are kind of these filaments and voids, and dark matter aligns with those. So even if you see all of the light matter around that, there's dark matter, and then there are spaces where there's nothing. So somehow gravity and whatever interaction dark matter is having with that light matter, it is kind of helping with that clumping, but I'm not sure we actually have the absolute answer of how everything has come together.
Yeah, we have hardly any idea what it is and where it is, but there is the idea that which I thought was a nice image of because in your book you said that dark matter has to be at least dispersed around the outsides of these big spherical halos around galaxies. So it was like an eggshell around the thing around the galaxy, and then the center is this, what we see as the galaxy, but that's a pretty big eggshell around it.
Yes.
Something
absolutely.
Like that, but not much more known. Okay, so one from George Steffner, a question. When were black holes in the center of galaxies first recognized, or when was it first guessed?
Right. That's an excellent question. So there were a lot of hypotheses about galaxies, but the first evidence that black holes actually existed kind of didn't really emerge until the 1970s, right when Vera was starting to do some of her work on dark matter. That's really when you have some of these first observations of kind of random X-ray flares that then were traced to the idea that you had to have some center mass that we can't see, drawing all that in and kind of creating or generating those emissions. And so that was the beginning. It was probably right around 1971, somewhere in there. And
that was pushed back on too, and people didn't, but people pretty much accepted it by the 90s that there probably were black holes at the centers of galaxies. We interviewed Heino Falke a couple of months ago, the guy who did the first picture of the black hole, or his team.
Oh, that's excellent.
Was very, very fascinating. All right, so Barbara Sink asks, it is my hypothesis that dark matter is what creates or holds the substance from which matter is produced. Thoughts?
Oh, that is an interesting idea. It definitely creates these gravity wells where you then can have some more interaction of light, the matter we can see, that kind of light matter. So yeah, that's definitely a good hypothesis, and that does align with some of the ideas that are out there, is that you kind of create some of these pockets of dark matter where then there's the interactions that lead to other types of matter that we can see.
All right, here's one from George Steffner, which if you can answer it, you will get a Nobel Prize.
No pressure.
I now suggest that time is just an artificial independent mathematical language variable representing Earth rotation. Existence is momentary, only there is no future or past.
I think that's a deep one.
I
don't know that I have the capability to answer that question. I might leave that one to the experts.
Well, there's a lot of interesting ideas about that out there, about time. Obviously, some people think that everything is created anew every moment, or that each moment is independent, and that idea has been investigated quite often. But the problem with that idea is that there's no continuum of momentum. And therefore, where would all the energy come from to create the new momentum each time? It's much simpler, and therefore, with Occam's razor, to say that there's a continuum of change going on, and not these moments that you could, of course, always, because we represent it mathematically, you can always cut it down smaller and smaller as time. But that's just a mathematical thing. There is no slice of time that you could do, no matter how small, that there'd be no movement or no momentum going on, because it's a continuum. The fact is, the continuum is always in the present, but maybe the past and the present aren't actually, non-existent. They are the previous version of the continuum and the future version of the continuum. But all the stuff is always in the present. I always find, from a philosophical point of view, the interesting part of that question is we have these visual imaginations. And so we think of our childhood, and we go back to that home that we were in, and we visualize it, and we say, I could go there. I could travel in time. That's why time travel is so popular. Right? But I could go there. But you can't really go there. All the stuff that made up that house is doing other work now. We know that every 7 years, almost everything in our body is off doing something else, and we have new parts, but it looks like we've got the same thing. So our bodies are a little like a solar system, stuff coming in, coming out, et cetera, et cetera. So it's a fascinating question, and I'd like to talk about a few other things, because you're a science writer like this, looking at different analogies. One of the things that I find fascinating about the whole investigation of the universe and the galaxies, first of all, is that we're always saying, I look back in time when we see a galaxy from before.
Right.
But you never really look back in time, just from what this question was about. You're always in the moment. What you see is a photon that has arrived here, and you have assumptions based on our knowledge and our theories that tells you, what does that mean? It means that has come from a galaxy 80 million light years away, and it took off at that time, but we don't see the past any more than if you go out into the Rocky Mountains and you look at the strata and you say, oh, I'm looking back in time because 80 million years ago this happened, and we just know that. People didn't used to know that. They didn't
No,
look at the
absolutely.
strata and say that's what it means. And I
Yeah.
think it's very important in science in general I mean, the difference between science and intuitive belief is that you want to have evidence. You
Right.
you don't want to just say, like in this case, there's the analogy of the eggshell around the galaxy was funny for me because there are, people who, their mythologies of the creation of the universe was an egg that was opened up, and stuff like
Right.
that. And I'm sure there are people who will jump to the conclusion, see, I was true the whole time. It was an egg,
Yeah.
because there's this eggshell. But those kind of intuitive leaps are very popular, but they're not very persuasive.
Yeah.
They're not
No, it's
persuasive
true.
to scientists. So you have to have something reliable going on.
Right.
So we don't. It'd be nice, like you said. You talked about science writing, and I thought really useful to have as clear versions of these explanations of what the scientists are doing.
Yes.
For everybody else to understand, because popularized versions that mash the ideas together. People have a basic belief about what Darwin's theory means, which is a popularized version of Darwin's theory, and it doesn't have almost anything. It has something to do with what he said,
Right.
but it doesn't have a lot to do with it. The eugenicists walking off in this direction, and another group
Right.
walking off in this direction. They take a piece of it and say, "Well, I understand that," and then they walk off with it. But that's not what he really said. And I think science writing about these big topics that people are fascinated that somehow touch on why we're here and all that kind of stuff. It's crucial that they be as clear as possible of what was actually
Yes.
said in the theory and not. Because if it's mushed up, everybody wants the mushed up version because they can't do the original version, right?
Right.
And so they're
Absolutely.
going to walk away with a mushed up version. So first of all, thank you for being a science writer who does it clearly. That's a very valuable tool. And second of all, now we talk about some of the ideas from your point of view of looking at this. So we look at, the idea of taking the galaxies from what we think of them, what we see, these spirals, and they're not all spirals, but they're in different form. Oh, before I go into that, I wanted to have you talk about one thing. It just reminded me when I got into the galaxies. There is a galaxy, you said, that part of it is going clockwise and part of it is going counterclockwise. That's so unusual. Can you say a little? Do you know anything about that? I just thought, did two smash together going in different directions and they haven't worked it out yet, or it's just such a weird idea?
Yeah, no, you're exactly right. That's exactly what happened. Was you had a galaxy merger, and some of the stars kept going one way, and some of the stars kept going the other way. And of course, you don't see the dark matter interact. You only kind of get the residue of the matter we can see, the light we can see. And so, that's exactly what's going on with that galaxy. Is you had a collision, and that's actually one of the really cool things about studying galaxies is sometimes you have to do a bit of forensics work to see. It's kind of like studying, unfortunately, like a car crash or some type of accident.
Right.
You have to kind of go back and piece things together to really understand what's going on. And Vera did a lot of that in her own work. She really looked at each galaxy as an individual and tried to understand its different characteristics and its different traits, even though the broader theme was that they all acted in a very similar way.
And now I'm going to go right off what you said about the forensics car crashing, because this was an idea I wanted to bring up. So there's a lot of assumptions in science about physics and the universe and the Big Bang and everything that are interesting to me. But if you go back to forensics, if there's a bullet shot and it fragments in a certain way, they have an idea about how it started, right? And if there's an explosion and it all goes out one side of the car, then they have some pretty good idea, why didn't it go out the other side, or what must it be made of? And so there's all this knowledge that we develop over time to try to think things through, right? So now we go to the Big Bang. Obviously, we're not there at the beginning, but we have all this evidence of what it's like. And a lot of the arguments are about how come it didn't come out smoothly? How come there's clumps?
Right.
How come? And a lot of the theories are about explaining why would there be clumps. But if we, and they almost always say, you can't look past the Big Bang.
Right.
Because we have no evidence for anything past the Big Bang.
Right.
But 150 years ago, someone could say, I can't look past the surface of a rock because we have no
Right.
evidence of that. But actually we find out, well, there's all kinds of pieces of why it turned out the way it did that tells us something about those rocks. Now,
Yeah.
what if those clumpings and so on explain to us what was happening prior to the Big Bang? And that's why it clumps, because that's some more like what forensics are in explosions that we do now. If you said, just an example, say the Big Bang is was a huge black hole prior to its explosion, and it condensed smaller and smaller and smaller and smaller and smaller until it came to the level, wherever that level is, that it would explode. And it's basically an empty space because it's collected all the material around it. But there probably, it probably will explode before all the material comes in. So there's like something like the Magellan Clouds coming in when it explodes. Yeah. Then when it explodes, there's an explosion, but there's a little pieces already there, and then they all get blown out, and that would, first everything would go in the direction it was going, and that would tell us something about it. In addition to that, there'd be these unusual things which would tell us there probably was some matter that wasn't in the material that exploded, et cetera. So
Right.
I know that that's an unusual way of looking at it.
Yeah.
But it seems to me that we do have some evidence, and it'd be very hard to piece together, et cetera, but we do have some evidence that we try to explain, like the inflationary universe idea is there because this all happened so quickly. But that seems to be based upon the idea that nothing was there before.
Right.
And I don't see why that assumption is made, because that's basically saying out of nothing, this huge explosion happened, when that might have happened, that could be true. But all other explosions come because
Right.
of the
There's
momentum.
something.
Everything
Yeah.
else we see comes from an explosion. So that's one thing that people could say, hey, we can actually go past this by seeing, because we're always going past what we see based upon
Right.
our assumptions. The other thing is very interesting in your book about the halos around galaxies, these huge, because the most common structure, it seems to me, at almost all levels, and they're all different at different levels. It's not just like fractal, that it's always the same at different levels. But the most common structure seems to be a sphere, and it's more diffuse around the outside and more concentrated towards the center. As we were saying before, the solar system is 99.8% of the matter is in the sun, and then there's just a few planets that don't really mean anything, including ours.
Right.
Relatively
Right.
speaking. Whereas in the galaxies, it's under 1% that's in the center, and that is also interesting to me, because if you look at the galaxies with the black holes, if we don't understand black holes correctly, if we're like two orders of magnitude off, that's all it takes to put it all right back into normal matter again, and no dark matter, right? Because so it seems to me that that's about all we're off, which is fascinating that we can get that close from so far away. I mean, it's amazing that we can figure out what happened to the rocks. It's amazing that we can figure out that there's all this information out there that we're analyzing, and it's all left over, and it's all right here, and we're analyzing, and we're the ones that are pushing back to what the causes and effects were, instead of pushing back in time, right?
Right. Absolutely.
So in your story about this, were there any ideas that came up that when you were writing it, that you said, I wonder if that makes any sense, or I wonder, because this is what Vera did all the time, right?
Right.
And I think that's one of the great things about her story, is she's always saying, well, that's the answer you guys have. But I'm not so sure that that's the right answer, sort of thing.
Yeah.
And did you, when you talked to her, was she still like that when she was, in her 70s and 80s?
Oh, yeah. I mean, when it came to dark matter, she completely kept an open mind that maybe dark matter doesn't exist. She was very open to that. And again, kind of just always questioning assumptions. What is the universe really doing? What is this dark matter? She had questions about dark energy. She didn't study it herself, but it was something that was very curious, because now we're talking about the majority of the universe being dark, just something that we, just forces and particles that we don't understand.
Right.
Which I think is the beauty of science, right? Every time you find something, you open up a bunch more questions. And so I think that's what kept her going, was just, what are those questions? And yeah, I think that's just how her mind worked, is always challenging the assumption.
Yeah, and those are the ones who break through, because
Mhm.
it's very hard unless you keep asking, because everyone's going to tell you stop asking those questions. It's like asking
Right.
the question why when you're 3 years old, to your
Yeah.
parents. At a certain point, everyone's always saying, stop that. We all believe this thing over here, and ironically, to me, it's like even in science, there's this sort of religious attitude towards the ideas that are already there.
Right.
There's an assumption
Yeah.
of authority and so on and so forth. And I think emotionally we're not quite scientists yet, but we're getting there,
Right.
and we're getting closer and closer, and
Right.
that's why we're making so much progress. And I'm just a fan of saying it's that attitude that's going to make us learn more and more and more and more. And you can have a great deal of respect for Isaac Newton, for example, and say,
Yeah.
amazing what he did, especially at his time against everybody else, all that kind of
Right.
stuff. Much better than somebody who even comes up with a clear idea now, because he was pushing against so many other forces. And at the same time, you can say, but all of his numerology work on the Bible, I'm not interested in, right? He can have other ideas that are worthless to the rest of us. It's an intuitional thing that he found more exciting than what he was working on,
Right.
but obviously didn't crack it. And I think it's a little tough in our society where anybody steps one step out of what somebody doesn't like, and then their whole contribution is suspect. I think it's right that we should be suspicious about people.
Yes.
That's absolutely part of the scientific thing. But in any case, you can respect the contributions of people and still disagree with them, like Einstein did.
Yeah.
I think that's the real scientific thing. You don't have to hate the people who got it wrong before or whatever.
Right. No.
Because
Yeah.
there's going to be someone 100 years from now that's going to be saying the same thing about you, whatever you come up with.
Right. Exactly. It's just always asking the question.
Yeah, ask the questions. And we keep, the speed at which we're improving is wonderful, but we know how much more we have to go. So I've got one more question here before we finish up. This is from Stuart. Can dark matter be regular matter from other non-three-dimensional parts of our universe, just like the 2D flatlander would be influenced by the 3D parts of objects which affect them, but which they cannot see?
I think that's a viable hypothesis. I mean, I think that's the thing, is like we have to kind of throw all of those ideas out there and then do what Vera did, start to collect data, start to figure out kind of what can we rule in, what can we rule out, what are other ways of looking at this, right? I think because dark matter, the search for it has been fraught with challenges. It's always good to keep those other options out there and keep kind of pulling on them. Even the idea of modifying gravity, MOND, those are all things that we have to keep thinking about and keep pressing on. And that's the only way we're going to get to the answer. If we just, like you said, make the assumption and kind of rule out any other type of idea, we could be kind of going down the wrong path. So I think it's important to explore all of these ideas and either collect data that support them or overturn them.
And Vera did that too, because you mentioned this story when she was, either in her 70s or 80s already at a conference, and then somebody asked a question, and she said, well, MONS, which is this modified thing, that also is something we shouldn't give up on.
Right.
It might have an answer. And it's the big thing in physics, of course, is both quantum mechanics and relativity theory are both very, very valuable, but we know that they don't mesh.
Right.
So it just seems we can say, okay, they're both brilliant, but something about them we don't understand, and it might be that one is right and the other is wrong, but it might be that they're both wrong, and that there's another way of looking at it that both are now explainable. And there's been a lot of wild speculatory things, but that's the advantage of science. Everybody can speculate, and if they're very intelligent about it and have some reliable evidence and some data for what they're doing, then they're going to get other people to listen. And they should just hang in there for at least 20 or 30 years like Vera did, right?
Yeah, exactly. Exactly. Yeah.
Yeah. Well, thank you very much, Ashley. That was really great. And I'd like to again thank the Bernard Osher Foundation for supporting this Good Lit thing, and also the Wonderfest Science Foundation. And so ends another event of the Commonwealth Club. in its 119th year of enlightened discussion. Thank you for joining us.
Thank you.
Thanks, Ashley.